This is a video for AP Statistics Chapter 7, and this chapter is about random variables. So basically we're taking the random probability from Chapter 6 and we're throwing some variables back into the mix to, create some more problems. So the first thing you need to know is the differences between two types of random variables. And one type are called discrete random variables. And with discrete random variables, you're able to list the outcomes. And then there's a different type, continuous random variables, and that's where you aren't able to list all the outcomes. And so an example of a discrete random variable would be, say, the number of heads when you flip a coin, and so with that, it's a discrete random variable because you can only have a positive integer number of heads, or you can have zero. So zero positive integer number of heads. Like you can't have 3.5 heads out of 5 tosses. And with a continuous random variable will be, say, the height or the weight of people. Because with that, you're going to have very small differences between people, especially over a large population. You're going to have, everybody's going to weigh a little differently than somebody else. And so also something that's covered in this chapter is a probability distribution. And one of the most important things to realize is that it must add up to 1. All of the different events, or all of the different outcomes of an event, the probabilities must all add up to 1. And so this is just an example I made up. So there's outcome that you get a 1, a 2, a 3, or 4, and these are just random probabilities, and they all add up to 1 because that's a probability distribution. And here's graphs I drew of what would a discrete random variable distribution look like, and then a continuous one. Because discrete, you're going to have, exact numbers right here. It's not kind of flowing like a continuous one is. And then something that's also important is calculating expected values. And so here's our basic formula is mu equals the total number times the probability. So here's another way to write this would be mu equals sigma xp. So let's say these are our two prob. So let's say these are our numbers. So x is 1, 2, and 3. The probability is 3.3 and 0.4. So how we would set this up, we would do mu equals, and then we would do 1 times 0.3 plus 2 times 0.3 plus 3 times 0.4. And that's going to equal 2.1. So this is going to be mu. And then another subject matter is the law of large numbers. And this is kind of a repeating term. It's going to come back in more chapters, and I think maybe we might have already addressed this. But the law of large numbers is as n increases, the sample mean will approach the population mean. So just an example of this that will kind of clarify and help make more sense is, say, let's flip a coin 3 times. So we're flipping a coin, flip a coin 3 times. Let's say we get 3 tails and 0 heads. The probability of having a head is 0.5. The probability of having a tail is 0.5 because there's only 2 outcomes, and with a standard coin, it's going to be an equal number. So, but we're only doing this 3 times. So you're not going to suspect that there's something wrong with the coin if you get 3 tails. You're just going to say, oh, guess, this side was just a little luckier that time. You're not really suspicious. But if we flip a coin 100 times, then you're going to expect to get a number of tails around 50. Let's say you get 53 tails and 47 heads. That's a pretty reasonable number, and that could happen because it's 100 times. But if we did 100 times and the number of tails was 20 and the number of heads was 80, then you're going to think there's something maybe a little suspicious because that's a big discrepancy. So notice as the number of trials, n, approaches the population mean, in this case, you can flip a coin infinite times, it's going to become closer and closer to around half because that's our probability. And so also something that we discuss in this chapter is calculating the standard deviations of two different things. And so even if you're adding and subtracting different sets of data, you're still always going to add their standard deviations. And also what you have to keep in mind when you do this is that you always square it so that it's the variance, because you can't add and subtract standard deviations. You have to add and subtract the variances and then square root it. So if you're adding together two standard deviations here, or two variances, so you're going to take standard deviation squared plus different standard deviation squared equals this, and then if you want the standard deviation, then you can just square root it. And same thing goes for here, even though you're subtracting. And this makes sense because when you add two sources of data together, you're going to have even more variation between the two sets because they're different. It's going to be more discrepancy. And so when you subtract it, if say here we decide to subtract it there, that's going to create less variation and a smaller standard deviation. So you're always going to just remember, always add it when you're comparing two standard deviations.